Welcome you all for the today classes. So in this classes, we are going to start the new topic, that is the application of Bernoulli's equations. So in the previous class, we discussed about the Bernoulli's equations and Euler's equations. Okay. So in today classes, we are going to start the application of the Bernoulli's equations. So first we go through that Venturi meter. Okay. Venturimeter is a device which is used for the measuring discharge in a pipe. So this is one device. Venturimeter is a device which is used to measuring the discharge or measuring the flow rate in the pipe. Okay. So there are some instruments which are used to measure the discharge or the flow within the pipe. Okay, those are the venturimeter, orifice meter. Okay, so these are the measuring devices. It will use to measure the flow rate or discharge in a pipe. Okay, so that is the first application of the Bernoulli's equations. Okay, so how to apply that Bernoulli's equations to this venturimeter devices, that is the application. Okay, so now here this figure shows the schematic diagram of the venturimeter. Okay, so mainly it consists of three parts. It consists of the three parts. One is those are inlet or convergent zone. So this part is called as the inlet or convergent zone. Okay, and this is the throat. So from this point to this point it is a throat, and from this point to this point it is a divergent part. So it consists of three parts, mainly three parts. So one is convergent, throat, and divergent. Okay, so in this venturimeter we always observe that this divergent part should be more than this convergent part. This whatever the length of this divergent part, it should be more than the convergent part. Okay, and in between these two parts we are having the throat section. Here it is the throat section, and to this convergent part we are connecting with the pipe, and here also it will connecting with the pipe. This is the divergent part, we can connecting this divergent part with the pipe. Okay, so venturimeter, what is the venturimeter? Venturimeter is a device which is used to measuring the discharge or flow in a pipe. That flow should be within the pipe or it is in closed system only. Okay, so at that time we are using these devices to measure the discharges. It consists of three parts: inlet, throat, outlet. Okay, so now the inlet section venturimeter is same diameter as that of the pipe. So whatever this inlet diameter, it should be same as that of the pipe which is connected to this divergent part. Okay, to which it is connected, followed by the short convergent section. So this is the short convergent section. Short convergent section, the entry of this convergent section, it should have same diameter as that of the pipe. Okay, so in this figure, say for it is the d1 diameter, it is d1 diameter. Okay, now it is a short convergent part, it is a short convergent part. Okay, so here with the converging cone angle of 2 L 21 plus or minus 1, 21 plus or minus 1 degree. The angle of this convergent part is 21 plus or minus 1 degree. So that angle here, this is the angle. This angle is if you draw one horizontal line here, this angle should be what? 21 plus or minus 1 degree, plus or minus 1 degree, and its length parallel to the axis is approximately equal to 2.7 into uh, capital D minus small d, capital D minus small d. Okay, so that this capital D is nothing but the diameter of the pipe, and this small d is nothing but the diameter of this throat, diameter of this throat. So that the length of this convergent part should be calculated by using this 2.7 into capital D minus a small d. So this will gives the what convergent part length, convergent part length. Okay, and where d is the pipe diameter and small d is the throat diameter. So here 2.7 capital D minus d so which will gives the length of this convergent part, and that capital D is nothing but the pipe diameter and small d is nothing but the convergent part diameter, this part. Okay, this is the next. Okay, next one. The cylindrical throat is a section of constant cross section. Okay, see this. So this part is the constant one here. This is the constant part section. That is the cylindrical throat section. It is in the cylindrical form. Okay, is section of constant cross section with its length equal to the diameter. So whatever the diameter is there, this diameter that is equal to this length. That same length and diameter of the throat is same here. So whatever the length is there, so it is having the same diameter of the throat. Okay, uh, the flow is minimum at the throat. Usually the flow is minimum at the throat. Diameter of the throat is perpendicular to the pipe diameter. Diameter of the throat is perpendicular to the pipe diameter. Okay, so this perpendicular to the diameter. A long divergent section with a cone angle of about 5 to 7 degree. So this is the long divergent section. So first it consists of three parts: convergent, throat and divergent. Convergent angle is 21 degree, 21 plus or minus 1 degree, and this divergent section, so that is uh, a long diverging section with the cone angle of 5 to 7 degree. So this is the 21 plus or minus 1 degree, and this the angle of this one is 5 to 7 degree, where the fluid is retarded and a large portion of the kinetic energy is converted back into the pressure energy. So this is here why it is large. Here the energy transformation takes place. Which energy to which energy? Kinetic energy is converted back into the pressure energy. Kinetic energy is again back converted back into the pressure energy. See here the energy is, that's why the divergent part is so large. This is the, this is about the venturimeter, and this is very important in your fluid dynamics. Okay, this is very important in your fluid dynamics. So next move on to the principle of venturimeter. Principle of venturimeter. How this works, on which principle it is worked. Okay. The basic principle on which venturimeter works is that by reducing the cross-sectional area of the flow passage, a pressure difference is created between the two sections. This pressure differences enables the estimation of flow rate through the pipe. See here, if you change the cross sections here, it is the cross section of the pipe is here it is different, and the cross section is here different, and again the cross section of the pipe is different, and this is the cross section. By changing the cross section, by changing the cross section or by reducing the cross sectional area of the flow passage, a pressure differences existed, it is created. So between the two sections, the pressure difference created between the two sections here, two sections. Okay, two sections. This pressure differences enables the estimation of flow rate. By creating the pressure differences, we can estimate the flow rate. We can estimate the flow rate. This is the basic principle, working principle of venturimeter. By reducing the cross section, by reducing the cross section, we are going to create the pressure differences. We are going to create the pressure differences between the two sections. So that will enable us to estimate the flow rate through the pipe. This is the principle of venturimeter. Okay. So next, expression for the discharge through venturimeter. So first, what is the venturimeter, and how many parts which includes, and on what principle it is worked. So now move on to the expression for discharge through the venturimeter. Okay, so here again we can draw the venturimeter. This is the inlet, this is the throat. Okay, uh, so here let d1 is the diameter of cross section 1. This is the section 1 1. So that is it is having the diameter of d1. P1 is the pressure at cross sectional at 1 1. So here it is a P1. V1 is the velocity at section 1 1. P1, D1 and P1. A1 is the area of cross sectional at 1 1. Area at cross sectional 1 1. Similarly D2, P2, V2 and A2 by corresponding values at cross section 2. So this is cross section 2. Here D1, P1, V1, A1 and D2. Okay, so these are the values with respect to the cross sectional 1. Similarly, D2, P2, V2 and A2 be the corresponding values at cross sectional 2. Okay, so now by applying the Bernoulli's equations between 1 1 and 2 2, we have P1 P1 divided by rho g plus V1 by V1 square by 2g plus Z1. This is at cross sectional 1, which is equal to what? P2 by rho g plus V2 square by 2g plus Z2. Okay, this is the Bernoulli's equations applied to these two sections 1 1 and 2 2. Okay, now since pipe is horizontal, that is Z1 is equal to Z2. These two terms get cancelled here since it is horizontal, that is Z1 is equal to Z2. Now we left with P1 by rho g plus V1 square by 2g plus P2 by rho g plus Vt square by 2g, which is equal to P1 minus P2 by rho g, P1 minus, so just take this term to this side, P1 minus P2 by rho g, which is equal to V1 square by Vt square minus V1 square by 2g. Okay, so again simplified this, we will get that H is equal to Vt square minus V1 square by 2g. H is equal to Vt square by minus V1 square by 2g, where H is equal to rho 1 minus rho 2 by rho g. P1 minus P2 by rho g. So this H is equal to what? P1 minus P2 by rho g. So that's H is equal to what? V2 square, as it is here. Okay, is the pressure difference between the section 1 1 and 2 2. So that whatever this H is there, that is the pressure differences between the section 1 1 and 1 2. Okay, here from continuity equations we have A1 V1 is equal to A2 V2. Already we know that the continuity equation is A1 V1 is equal to A2 V2. So from this equations V1 is equal to, we'll get that A2 V2 by A1, A2 V2 by A1. Hence H is equal to this, if you substitute that V1 here, V1, okay, so it becomes what? V2 square by 2g into bracket A2 square minus A1 square divided by A1 square. Okay, if you simplified this, V2 is equal to this, V2 is equal to A1 into root of 2gh divided by A1 square minus root of A1 square minus A2 square. This is considered as equation number 1. So this V2 is equal to what? A1 into root of 2g divided by root of A1 square minus A2 square. Okay, if we simplify this equation, so we will get that this equation number 1. Okay, so next, substituting the value of V2 in the equation Q is equal to A2 V2, we have so q is qth is equal to, if you substitute that v2 value here, so already we have that v2 is equal to a1 root of 2gh by root of a1 square minus a2 square, but here discharge q is equal to what? A2 into v2. This value v2 is substituting from the equation number 1 here, this is a v2 is equal to, so from that we'll substitute that value, we will get that qth is equal to a1 a2 into root of 2gh divided by root of a1 square minus a2 square. So the above equations is for the ideal fluid and is called as a theoretical discharge equation of Venturi meter. For real fluids, the equation changes to Q actual is equal to CD. Just we have to multiply that CD to this equation, so we will get the actual discharges. That is Q actual is equal to CD A1 A2 divided by root of A1 minus A2 square root into root of 2GH. This is the Q actual, and this is the Q theoretical, and this is from this to these two equations we will get the discharge through the pipe by using the Venturi meter. Okay, so that A1 A2 into root of 2GH by root of A1 square minus A2 square will gives us theoretical discharges, and this actual CD into A1 A2 root of 2GH by root of A1 square minus A2 square will gives us the actual discharges. Okay, so now expression for H given by the differential manometer. Okay, so here again we are having two cases. That case one is when the liquid is in manometer is heavier than the liquid flowing through the pipe. Suppose the liquid which are used in that manometer is heavier than the whatever the fluid flowing in the pipe. Okay, suppose if you are consider one pipe, inside that pipe the fluid is flowing. Okay, that is heavier than the whatever we use that fluid in the manometer. So that is one case. Here it is case number one. Okay, so in usually we know that in a differential manometer we are having the fluid. Okay, so that fluid, the liquid in the manometer is heavier than the liquid flowing through the pipe. Suppose inside the pipe water is flowing, so we have to use that use the liquid in the manometer, that is mercury. So always it should have the different density. Okay, if inside the pipe, the water is flowing, then we have to use the different liquid in the manometer. Suppose if inside the pipe the mercury is flowing, then in the manometer we should use the water as a fluid, so that density of that both the fluid is it should be a different. Okay, so that is here in this first case what happens when the liquid in the manometer is heavier than the liquid flowing through the pipe, so that H is equal to X summation of SH by S naught minus summation of 1. Okay, where SH is the specific gravity of the heavier liquid. SH is specific gravity of the heavier liquid. Similarly, S naught is the specific gravity of the light liquid, or liquid flowing through the pipe. So that's a specific gravity of heavy liquid to the specific gravity of liquid which is flowing through the pipe. Okay, X is the difference in the liquid column in U2. X is the difference between in liquid columns in U2 manometer. Okay, this is the equations. And case number 2, when the liquid in the manometer is lighter than the liquid flowing through the pipe. Reverse this case of this first case one. Okay, so here that we in that case uh, this H is equal to what happens here, summation of phi minus SL summation of SL by S naught, where SL is the specific gravity of the heavier liquid. Okay, and this S naught is the specific gravity of the liquid flowing through the pipe. Okay, and X difference in the liquid columns in U2. Okay, so here uh, expression for the H for differential manometer. So when the case one is when the liquid used in the manometer, it is if it is heavier than the liquid flowing through the pipe, we can use this expression for the H to find out that H. If when the liquid used in the manometer is it lighter than the liquid flowing through the pipe, then you can use this expression for the H values. Okay, so in the today classes we discussed about the first application of the Bernoulli's equation, that is venturimeter. What is the venturimeter, and what are the sections which involved, and working principle, basic working principle of venturimeter, and expression for the Q discharges, and also expression for the H for given differential manometer. Okay, so with this we completed the today classes. So in the next class again we will start the another application. Okay.